Hello, grade 10s. Today we continue with matter and material, but we are starting a new topic called the atom. This is the third chapter of 5 chapters under the topic of matter and material. Now, in this section, we are going to understand what relative atomic mass means. We should already be familiar with atomic number and atomic mass of elements based on the periodic table, but we'll revise that. And again, based on the periodic table, we are going to be able to determine the number of protons, electrons, and neutrons in elements. We're also going to determine the number of electrons and charge on an ion after removing or adding electrons to an atom. Now, ions are a new concept in grade 10. All the way to the end of grade 9, our assumption was always that atoms are neutral. And now in grade 10, we are starting to deal with atoms that are not neutral because they have an excess or a deficit of electrons. And atoms that have a charge on them are called ions. We're also going to define isotopes, and we're going to calculate the relative atomic mass of elements from the percentage of each isotope in that sample. We are going to represent atoms and ions using E, Z, and A notations. We are going to describe what energy levels, shells, and orbitals mean. This is around an atom, and this is where the electrons live. We're going to use Aufbau diagrams and spectroscopic notations to represent the electron configuration of the first 20 elements. And we're going to differentiate between core electrons, valence electrons, and valency. The first thing that we need to understand is that atoms have really tiny diameters. What is a diameter? Well, if this is a circle, the diameter is a line from one end to the other end. Half of that length would be the radius. Atomic diameter is very small. The mass of atoms is also very small, which is actually why we rather deal with the relative atomic mass, which is what we're going to understand here. So, as we can see, atoms have tiny diameters ranging from 1 times 10 to the minus 10 meters to 4 times 10 to the minus 10 meters. So this would be the diameter of the smallest atom, and this would be the diameter of the largest atom. But we can see that these are really, really tiny numbers. The reason that we deal in meters is because meters are the SI unit for distance, and there'll be a separate video on SI units. So if we want to take 1 times 10 to the minus 10 meters and just try to put it in perspective for ourselves, if you take a 1 meter line and you divide it into 10 billion equal parts, one of those parts will be equivalent to the diameter of the smallest atom, which happens to be helium. And later on, we're going to understand why helium is actually a smaller atom than hydrogen. But we can't even conceptualize this, and we cannot see it under a microscope in any kind of detail. So atoms are small. Atoms also have very small masses. So if we look at 4 elements here, hydrogen, which is the lightest element, carbon, oxygen, and uranium, which is the heaviest natural element, well, we can see the masses here that are measured in grams are really tiny values, times 10 to the minus 24 for the lightest atom, and times 10 to the minus 22 grams for the heaviest atom. So we don't need to memorize these numbers, but we do need to take away from this that the mass of an atom is really tiny, and working with these numbers would actually be quite difficult. So the atomic mass of hydrogen, which is the lightest element in grams, would be this value over here. And uranium, which is the heaviest natural element, will have this many grams in mass. I'd like you to watch this video because it will really help you to conceptualize the extremely small size of the atom. And I'll put the link to this video in the description. Now, we're dealing with extremely small numbers, and like I already said, these numbers would be really, really difficult to work with. So we prefer to work with a relative atomic mass. A relative atomic mass allows us to convert these very confusing numbers into very simple numbers. So let's understand what that means and how it works. So I made up an imaginary scale called a baby scale. And I've said that on the baby scale, a 3 kilogram baby would receive a value of 1 unit on the baby scale. So if somebody has a mass of 6 kilograms, what is their mass on the baby scale? Well, 3 kilograms is 1 unit, so 6 kilograms must be 2 units on the baby scale. And the way that we work it out is we say 6 kilograms divided by 3 kilograms. This is our scale value, and that gives us 2 units on the baby scale. Note that there are no units of measurement because 6 divided by 3 is 2, and we cancelled out the kilograms. A ratio doesn't have a unit of measurement. So if someone has a mass of 52 kilograms, what is their mass on the baby scale? Well, again, now we need to say 52 kilograms divided by 3 kilograms, and that gives us 17.33 units on the baby scale. So you can see that using a scale like this kind of gives us a relative mass. Well, if the mass of one baby is 1 unit, then something that has a mass of 2 units on the baby scale is the same as the mass of 2 babies, and something that has 17.33 units on the baby scale, well, that has the same mass as 17.33 babies. Now, that mass can also be lower than the scale value. So if someone has a mass of 1.5 kilograms, what is their mass on the baby scale? The formula remains the same, 1.5 divided by 3, and that gives us 0.5 units, or half a unit on the baby scale. In the same way, scientists decided to take a carbon atom, which is called a carbon-12 atom. As per your periodic table, the number above is 6, which represents the number of protons, and the number below is 12, which represents the number of protons and neutrons. Now, we know that protons and neutrons have a mass, and we know that electrons don't contribute to the mass of the atom. So carbon-12 has a mass of 12 units on the atomic scale based on the number of protons and neutrons that exist in its nucleus. So if we use carbon-12 as our reference point, if we take this entire mass of carbon and we divide it by 12, then we get the value of 1 unit on the atomic scale. So 1 unit on the atomic scale in real life is equal to 1.658 times 10 to the minus 24 grams. This is not a number that we need to memorize. We just need to be familiar with the concept of the atomic scale so that we can understand the relative atomic mass values that are given to us in the periodic table. So this value over here is approximately the same mass as 1 proton or the mass of 1 neutron. Protons and neutrons have the same mass. Now, because a hydrogen atom is made up of 1 proton in its nucleus and 1 electron in its orbitals, and it has no neutrons, and electrons are negligible in mass, then this is approximately the value of one hydrogen atom. So this means that this value in grams of an atom receives a value of 1 unit on the atomic scale. If hydrogen has this mass, this is hydrogen's real mass, what is its mass on the atomic scale? We're going to work it out in the same way that we worked it out based on the baby scale. So we take this value, our value of hydrogen's mass, and we divide it by our scale mass. And that is going to give us a value of 1.01 units on the atomic scale. Here we have the real mass of oxygen, and if we divide the real mass of oxygen by the mass of 1 unit on the atomic scale, then we get a value of 16.04 units on the atomic scale. And let's try uranium. We take uranium's real mass and we divide it by this value over here, and we get a value of 238.24 units on the atomic scale. Now, do these numbers look familiar? If you take a look at your periodic table, you'll see that the number below hydrogen is 1, the number below oxygen is 16, and the number below uranium is 238. So these numbers are usually rounded off in a periodic table as the atomic mass. So it's not given as a number with decimal places, but rather than a whole number. So hydrogen has an atomic mass of 1, oxygen of 16, and uranium of 238 as per the periodic table. So all we really need to understand from all these slides that I've just taken you through is that when we refer to the mass of an atom, we're not referring to the real mass of an atom measured in, say, grams or in kilograms, but we are referring to a really tiny relative mass on some tiny atomic scale, which gives us numbers that are easy for us to work with. Now that we understand that, let's move on to the structure of the atom. An atom is made up of protons, neutrons, and electrons. Those are the 3 subatomic particles that make up atoms. Now, this table over here shows us the mass in grams and the charge of each subatomic particle. What you're going to find is that the mass of a proton and a neutron is the same value. The mass of an electron is much, much smaller. We'll discuss that shortly, but this mass actually makes it negligible. And we can also see, well, neutrons have no charge. Neutrons just contribute to the mass of an atom, but the charge sits with the electrons and the protons. Electrons have a negative charge and protons have a positive charge. So the existence of one proton and one electron in an atom, they'll cancel each other out to have a 0 charge. An atom that is neutral, if it has 100 protons, it also has to have 100 electrons. Now, you can see that the charges are the same strength, even though the masses of electrons and protons are very, very different. Even though electrons are much smaller than protons, they still carry the same strength of charge as a proton. Let's note a few important points about the masses of subatomic particles. So, first of all, the mass of a proton is equal to the mass of a neutron. Secondly, the mass of an electron is so small that we say that the mass of an electron is negligible. So just to be precise, and you don't need to know this, but the mass of an electron is nearly 2,000 times smaller than the mass of a proton. So if you weigh 50 kilograms and you're standing on a scale, you want to check your mass, and you add a tiny little earthworm on your shoulder, is that going to make a difference to the mass that the scale reads? No, it's not. Therefore, we ignore the mass of the earthworm. That is equivalent to ignoring the mass of an electron. The mass of a proton is the same mass as a hydrogen atom, and that's because a hydrogen atom is made up of one proton, as well as an electron, but remember that we don't add on the mass of the electron. On the atomic scale, the mass of a proton is 1 unit, and the mass of a neutron is 1 unit, and the mass of an electron is 0 units. Now let's note a few important points about the charges of subatomic particles. Charges are measured in coulombs, and we're going to learn more about charge when we learn about electrostatics. Now, neutrons are neutral, so they don't have a charge. They just make the element heavier. They contribute to the mass of the atom. Protons obviously have a positive charge, and electrons a negative charge. And the value of the charge of the proton is equal to the value of the charge of the electron, even though their masses are very different. Now, protons and neutrons are found in the center of the atom, inside a very small and dense place in the atom that is called the nucleus. And around the nucleus, we have a large region where the electrons live. Where does the identity of an atom come from? The identity of an atom comes from the number of protons. So regardless of the number of neutrons or the number of electrons that an atom has, the number of protons ultimately decide the atom's identity. So any element that has 3 protons in its nucleus, regardless of the number of neutrons and regardless of the number of electrons that the atom possesses, it will always be a lithium atom. Any atom with 26 protons in its nucleus will always be an iron atom. Because the nucleus remains intact and the number of protons in an atom does not change, then the number of protons gives the atom its identity. On the other hand, electrons cannot give the atom its identity because electrons may hop off an atom or hop on an atom. And we'll understand that a little bit later when we learn about chemical bonding. Let's consider the diagram below representing a lithium atom. Here we have a neutral lithium atom. It has 3 protons in its nucleus and it has 3 electrons in its orbitals. Now, if an electron is removed from a lithium atom, the number of positive charges, the 3 protons, doesn't change, but now we only have 2 negative charges or 2 electrons. So that means that the positive charge is going to be higher than the negative charge. Plus 3 minus 2 gives us a net charge of plus 1. So now we know that the lithium atom that has lost an electron will have a charge of plus 1. Now this lithium atom is no longer an atom, it is now called an ion. An ion is an atom with a charge. And a positively charged ion, meaning an ion with a positive charge, has a special name, and that is called a cation. So one way to remember this is if you like cats, cats make you feel positive, so cations are positive ions. Now let's consider the diagram of a fluorine atom. A neutral fluorine atom will always have 9 protons in its nucleus, but also 9 electrons in its orbitals. Now, if this fluorine atom has gained an electron, it still has 9 protons, meaning 9 positive charges in its nucleus, but it will now have 10 electrons, so 10 negative charges in its orbitals. So in this case, the positive charge will be lower than the negative charge. So plus 9 minus 10 will give us a net charge of minus 1. Again, we have an ion because it is an atom with a charge. But in this case, it is a negatively charged atom. And so a negatively charged ion is called an anion. And you may think of it like an onion. An onion makes you cry, and crying is negative. So a negatively charged ion is an anion, which sounds a bit like onion. So in summary, an atom that loses electrons becomes positively charged. It is an ion because it's a charged atom, but it is a cation because it has a positive charge. And an atom that gains electrons becomes negatively charged. Again, it is an ion because it is a charged atom, but it is called an anion because it is negatively charged.